Thanks very much, Pablo. Thanks for the introduction. Yes, it's nice to meet you all. I think I might have met some of you in person last year. Um, Broadly speaking, I actually work in geodynamics. So I actually dip my toe into things that include critical minerals exploration. We do quite a lot of work here on forecasting sea level rise, so how sea level is going to respond to ice sheets melting and stuff moving forward. But today I'm actually going to be talking about some fairly new work that I've undertaken with some folks at ANU and with US military researchers on monitoring for underground nuclear tests. I'd like to acknowledge that I live and work on the ancestral lands of the Ngunnawal and Ngambri people, and I pay my respects to their elders, past and present. And I'd also like to acknowledge that Indigenous communities have actually been as usual, on the receiving end of some of the worst impacts of nuclear testing that has happened in Australia. So I'll talk a little bit more about that later. Yeah, I think that's an important point to make. So where does this whole thing start? Well, it started in the Second World War with the American development of the nuclear bomb, and it kind of culminated in the first test, which was the Trinity test. And it may well be some of you recently have seen this in the movies and so on, so you might know more about it than I do by now. But yeah, this was in 1945, and this really kick-started a global arms race that the main players were obviously the Americans and the United States, but there were several other countries around the world getting heavily involved. And that's reflected in this kind of, the graph here showing you this kind of ramp up in the number of warheads available in those two kind of countries. And you can see it really spiking through the Cold War kind of era. And then after the breakup of the USSR, things started to calm down. There was a lot of mutual work to decommission and reduce the numbers of weapons. But unfortunately, they are still a very relevant tool, I guess, in today's geopolitical world that we work in. So throughout that period, the US, the USSR, the Brits, the French were all conducting tests, and these tests probably, obviously at the time, but very much in hindsight, are responsible for causing quite a lot of damage, and damage that we will be living with for thousands of years in some cases. Some of the radionuclides that these things release have half-lives in the 10,000s of years. So this really leads to a lot of contamination and pollution. Yeah, unfortunately. So this map is showing you where those tests have occurred, the ones that we know about at least. And you can see that for the, particularly amongst the French, Brits and Americans, there was a lot of testing in our part of the world. And as I kind of already hinted at in that kind of acknowledgement of country, there was some, the Brits came and tested here in Australia in two different places, the Montebello Islands, but also here in South Australia, a place called Maralinga. And these tests contaminated a large swathe of land, and they were not undertaken in any way you would hope. The level of planning and forewarning for the local people that were around there was abject, honestly abject. So the people from around there are called the Anangu Pitjantjatjara people, and the lands that they lived on became so contaminated that they were only handed back, I think, in 2009 after the kind of various levels of cleanup. And also, they just weren't really warned. There was one person responsible for warning them. So he would travel around, literally drive around in his car trying to warn them. And in some cases, there was a case of an Indigenous family who were found camping next to one of the craters left after one of these tests. So yeah, it's kind of shameful piece of British and Australian history in a way. But the one I actually want to talk about, the test I do want to talk about more, is one that took place in the South Pacific in one of the islands here at Bikini Atoll. So this is called the Castle Bravo test, and it was undertaken on the 1st of March 1954. And it was a new type of weapon, which was, they were kind of experimenting with which radionuclides to put into these bombs. And this was the first test of what was called a lithium deuteride weapon. And there were a number of reasons that this went badly wrong. So the first thing was that the scientists completely failed to understand the chain of reactions that was going to be kicked off by this explosion. And in reality, there was an isotope of lithium that they thought was going to be inert and not really get involved. And it turns out it really did get involved. So the actual yield of this thing was 2.5 times bigger than they were expecting. There was also a change in direction of wind overnight before the test, and it started blowing towards the neighboring atolls that had populations. And that on its own should have been enough for them to say, no, we're not going ahead, but they did anyway. So those two factors combined to make a very large cloud of radioactive fallout that ended up raining out downwind over these atolls, these inhabited atolls, and there was something like 250 natives living here, and various also Americans and so on who were in the area for the test specifically. And all of them had to be evacuated, and there is a legacy of cancer and birth defects, and you can't eat the fish from there and all sorts of stuff. So really bad test. The only good thing about this is it really brought into a very public sphere that we should stop doing this above ground. We should not be testing our weapons in the on the surface of the Earth, where you can inject this stuff into the atmosphere, and it kind of it's relatively speaking uncontrollable where you end up polluting. And so this was one of the main kind of motivations to a treaty that was finally signed in 1963, called the Partial Test Ban Treaty. And what that did was, one of the main things it did is it said, we agree to no longer do tests above ground, in the atmosphere or in space or underwater. And it said we can only now test underground. So we have to dig down and test underground. One thing to note on here is that the French in red did not sign up to this, and they continued atmospheric testing right into the 90s. So, with all the effects that associate with that. So we had this treaty signed, and it had been, the people who signed it have adhered to it. And what it meant was that all testing moved underground. And what that meant is you had to be able to monitor for tests taking place when they were underground. And there became a lot of kind of international collaboration to start monitoring for these tests, work out who's doing it, where they're doing it, did they follow the rules, and so on. And there has come into being this system from today called the International Monitoring System. And so this is a global network of 4 different types of station that are continuously live feeding data back to the headquarters of the CTBTO, which is in Vienna, for monitoring purposes. And there are several different types of monitoring kind of instrument that are out there. So there are atmospheric samplers, and what they do is they continuously sniff the air, and they're looking to pick up any of the radioactive nuclides that don't occur naturally in nature, but are generated during the process of explosion through these bombs. So as soon as you sniff one of those, you know somebody has done a test and that material has got into the atmosphere. And there's one of these stations in Darwin. I think it was set up around about 2002, something like that. The Northern Territory is actually quite heavily involved in the IMS. There is also what's called an infrasound station at Warramunga. And the infrasound stations, they're designed to listen to the sound wave produced by explosions. So the sound traveling through the air, they're supposed to pick that up. And the final thing on this map, there are these 2 kind of pink boxes down through here. One's again at Warramunga and the other's at Alice Springs. These are arrays of seismometers. And these seismometers are out listening to the noise of energy that has traveled through the Earth from these kind of explosions. And just to show you what those arrays look like, so they have a footprint on the ground of roughly 20 by 20 kilometers, something like that. 24, 25 station kind of make up the network. The Warramunga one's got this quite interesting kind of L-shaped array. So it's quite good at recording energy coming in along either of those axes. And the Alice Springs one is more of a kind of conventional net kind of structure. So these are out there continuously listening to shaking of the ground that can be caused by nuclear testing. And so what's the challenge here? So the problem when we're trying to monitor for underground nuclear tests is that we have other sources of seismic energy that arrive on our seismometers. And in particular, one of those is earthquakes. So when you have this slip along the fault plane, you generate compression and extension in different areas of the kind of rock that's slipping, and that drives elastic energy that propagates away to make seismic waves, and you record them on your seismometers. And so we have this issue that there are an awful lot of earthquakes around the world every day, and there is hopefully no one doing any testing. So we are looking for what is potentially a non-existent needle in a haystack that's the size of the planet, with all these earthquakes going off all the time. So there's this major challenge that emerged. How do we differentiate tests from earthquakes? And geophysicists have been obsessing with this problem for more than 50 years now. And I'll just go into a little bit about how they do it and what the pros and cons are and so on. So some of the testing methods that have been proposed, the first is obviously to look at the location of the event. So if it occurs in what we recognize as being a plate boundary with a lot of earthquakes, then there's a higher chance that it's an earthquake. If it's somewhere that's normally aseismic and there are no earthquakes, then you'd be more suspicious of it. Obviously, that's not perfect because you can go and do your tests somewhere where there might be naturally occurring earthquakes. Another one is to look at the depth of the event. So generally speaking, it's quite hard to drill deeper than a few kilometers down into the earth. And so events that are happening at 10, 15 kilometers down are almost certainly earthquakes, whereas any kind of test would be confined to shallow depths. Again, the problem is we also have shallow earthquakes, so this is an imperfect approach. There was a method proposed that is relatively successful to look at the ratio. So this is the kind of picture down here showing you the arrival of seismic energy, in this case from an earthquake. And as time goes along, the first thing that arrives is you get what are called P waves coming in, and then you then get these S waves. These are both body waves, so they both travel through, they dive down into the earth and they travel through its interior, and then they come back up to the surface where your seismometer is. Then this big noisy thing that comes in afterwards is what we call the surface waves. And these are waves that are traveling along the surface of the earth, as the name suggests, kind of like the ripples on a pond when you chuck a rock in. So they kind of spread out, they're confined to the surface, and because they're confined to the surface, they actually don't decay as quickly, so they kind of travel a long distance away. And they have very high amplitude, so they generally have the largest motion amplitude associated with them. And that's why in earthquakes, it's these waves that tend to do a lot of the damage to buildings and so on. These are the ones that really get all the skyscrapers shaking and all this kind of stuff and do a lot of the damage. So that's what the surface waves are. So the method that was proposed was to look at the ratio of P wave energy to S wave energy. That turned out to work all right, but it didn't work as well as looking at the combined energy of these body waves versus the combined energy in the surface waves. Now, it turns out that earthquakes are really good at generating this surface wave energy, whereas explosions, like nuclear tests, tend to produce comparatively a lot more energy in this body wave area here. And so by looking at the ratio of body wave energy to surface wave energy, they figured out that you can, generally speaking, discriminate quite nicely between earthquakes versus explosions. And so people come up with equations like this straight line here that basically divide one from the other. So the idea is if you're monitoring for these things, you plug your seismogram through this kind of setup and say, yeah, this one's suspicious, that one's probably an earthquake. That became the state of the art for decades, and it's very successful. It works really well. But it all kind of changed with the North Korean test. So North Korea started testing, it did its first test in 2006. The most recent test was in 2017. And here, something funny happened where despite us knowing that they were tests being performed, they were not registering as tests on that monitoring procedure where we compare the body waves to the surface waves. The reason for that is because what the North Koreans did is they drilled into the side of a mountain and they tested inside the mountain a kind of level that was comparable with the ground level to either side of the mountain. And so what that did is it made the whole kind of mountain suddenly kind of sway around and kind of reverberate. And that generated a lot of surface wave energy. And so suddenly there was way more surface wave energy than normal being produced, and that's why the method failed. And that is why still today there is now ongoing research into what can we do to improve these monitoring methods. And that's where some of the work that I've been doing comes in. So back to the drawing board. 2017, we went back to the drawing board and we started to think again about this problem. And what one of the things people focused on, amongst many, was this thing called the moment tensor, seismic moment tensor. Now, I'm not putting this picture up to scare you. This is the kind of conceptually what a moment tensor is. What it does is it describes the forces that are operating at the source of the seismic event that you're monitoring. And those forces are what give rise to the deformation that we are then measuring on our seismometers. And you can mathematically represent it as this, what we call a 3x3 matrix. So each of the elements in this matrix corresponds with the kind of forces shown on here. So if you look at the ones on the diagonal, if you look at the top left one, that's basically extensional in the direction of the arrows. Number 2 on the diagonal is this one, that's perpendicular, so it's extension in the perpendicular kind of direction. And the third one is extension in the final direction, the up and down direction. And these three, therefore, are build you the full extensional space that you can do to deform your local area of rock when you make an event. These ones off to the side, the diagonal ones, basically correspond to kind of torque. So one face of your cube sliding sideways with respect to another face. The key thing here is, despite there being 9 of them, because in this system we have to conserve angular momentum, this matrix is actually what we call symmetric. So the one down here on the left is the same as this one up here. The one at the bottom left is the same as the one on the top right, and the one down here is the same as this one. And what that really means is that there are 6 unique numbers that go into this seismic moment tensor. So, sorry, that's a theoretical background to, we won't look at these again, I hope, but that's theoretical background to, can we look at the source of what's happening in these seismic events and use that information to discriminate between explosions and earthquakes? This is where, Paolo, during his introduction, had to say a kind of very long-winded name of another department here at ANU. At ANU, we have our statisticians all hidden away in the Department of Finance. And so I started working, I met her purely by chance, but I started working with a lady there called Janice Seeley, who is a world leader in the statistics or a statistical assessment of data sets, where these data sets are geometrically constrained in some way. And that sounds kind of odd, but most of us are used to looking at a graph of data, XY plot of data, and thinking the axes go to plus infinity and minus infinity in both directions, and your data plot could plot anywhere in that space. That's not true for these seismic moment tensors. They have what's called a geometric constraint, where they all have to sum up to a certain value. And that means the statistics you use has to completely change to your conventional statistics. And so this kind of nasty sounding phrase, one can consider unit vectors, it doesn't really matter. The point here is that our moment tensors are going to, every possible solution is going to end up sitting on the surface of a sphere, and that sphere exists in 5 dimensions. And that's the kind of complicated bit to get your head around. But try not to worry about it too much. Basically, there is a shape where every possible solution, every earthquake, explosion, collapse, whatever it is, sits on the surface of that sphere. And so what, we'll skip this. What people, so this is how you actually go about mapping your moment tensor onto that sphere. Again, it doesn't really matter in detail. What somebody came along and this is a pioneering paper from 2020, what they came along and said is, hang on a sec, I can use this concept of this sphere in 5 dimensions with all my data on it to actually differentiate between explosions and earthquakes. And so what they did is they basically had a finite data set. They had 23 explosions, 28 earthquakes. They mapped them into this kind of sphere on multi-dimensions, and they showed that they plot in different areas. And what that means is if you have a new event, you can compare it to these existing populations and say, yep, that one belongs in the explosion population. This one belongs in the earthquake population. And you're going to see a lot of this picture on the right here. We call this thing the fundamental loon. It's a way of plotting this data that's on a 5-dimensional sphere actually on a 2D surface. So it loses information as you project it down to a 2D surface, but it allows you to kind of see how the earthquakes down in through here are sitting quite separately to the explosions up in through here. Now, what basically these guys did is they said, right, the explosions are really concentrated. They're all really close together up through here. And so what we'll do is any new event we get, we'll look at the angle it makes between this explosion population and where it actually plots on the sphere. We'll look at the angle between the two, and we'll say, if it's larger than 30 degrees, probably was an explosion. The problem with the method was that when they then expanded the database and looked at more and more earthquakes and more explosions, there starts to become overlap in this space. And this is something that is, so our metric for determining whether something was or was not an explosion starts to break down. We all of a sudden start to include, either we start to include a lot of earthquakes, which we don't want, because we manually have to go out and check every single one of these events to say, was it an explosion or not? That makes a lot of work. For the US military, they can dedicate a lot of resources to it. They probably investigate a lot of earthquakes, a lot of events that turn out to be earthquakes. For somewhere like Australia, where we have a much smaller monitoring team, so in Australia, there is a group in GSA NT Australia who do some of this monitoring, but they have, a handful of people. They probably can't go out and look at 100 earthquakes. So they need a method that's going to do a better job of saying, these were the most likely explosions. Let's not look at too many earthquakes. And so that's kind of the balance you're really playing here. How do I not miss an explosion, but also not have to falsely look at a whole lot of earthquakes? And so the method kind of broke down when it got expanded to more data. And so, oh, this one's gone wrong. I don't know why this slide looks like this. Suffice to say, the point of this slide was really the picture on the right, which is to say one option you've got is to say, well, let's change that angle that we talked about. How far does my event plot away from the explosions? Change that angle and see how we do. And as you go through these databases, you can work out how many do you misidentify. So here was our initial 30 degree. You can see that for 30 degrees, we were missing out on nearly 20% of all the explosions. If we boost that thing up to 60 degrees, we're suddenly getting much better. We're getting all our explosions, but we've now picked up 10 or 15% of the earthquakes. And because there's so many earthquakes, that's actually a lot of events. We can be picking up hundreds and hundreds of events in the screen. And so this is where we came along. We came along and said, can we improve this thing? And what we did was quite mathematical and quite statistical. So I'm just going to summarize it. If anyone wants to hear about it, properly, I'll be very happy to answer questions in more detail afterwards. So yeah, please feel free to fire away if you want to know more. Yeah. So this is the paper that we published last year. And so there's Janice on the left, and Brent on the right there works for Los Alamos National Labs in the US, which are kind of a government research arm. So Los Alamos is actually where the Trinity and so on, the initial bombs were developed. And we made a few tweaks to this procedure that designed to make it more effective. The first one is that we started fitting what are called probability distribution functions to these databases of existing events. We use a different mathematical approach, which is called a Bayesian probability framework. So Bayesian, you might, if you ever interact with geophysics in general, you might see this word cropping up. It's basically a way of trying to get a better handle on the errors and uncertainties in your model. So normally speaking in geophysics, we have some data and we try and fit a model to that data. And the Bayesian probability is about trying to understand, there's a whole family of models that might fit the data. So what is my uncertainty in the model space that is still unknown because the data does not constrain it. So this is the kind of a branch of mathematics that we brought to this problem of this nuclear determination. And the third one is that we actually had to do something quite clever, which was all led by Janice. Janice is the genius here, with the shape of the probability distribution functions. I'll go a tiny bit into what I'm talking about there. So, okay, so this, for anyone who's mathematically minded, is how we represent these data on this 5-dimensional sphere. We basically break them down into the mean of all the data. So you've got this sphere existing in 5 dimensions, and all the data points plot on the surface of it somewhere. And if you look at the average point of where they all locate, that's the thing, this population mean direction. And what you can then do is you can then look down on the sphere at that point, and you can look at all of the residual variation away from that mean direction. So all of these other ones, it's called something called the tangent normal decomposition, but you can basically think of looking down on the top of this sphere at the middle of all the data, how much does it spread out in each of the remaining dimensions that we're worrying about? This is what the maths look like. You can basically construct this thing for these populations. And this is what that kind of concept of looking down on the sphere looks like. So if you look at for example, this E2 versus E3, what we've done here is we've gone to the surface of the sphere where the mean population is. We're looking down on top of it, and we're looking at how does the data spread out in the second and third dimensions. So you can see there's more data in the middle, and there's less data further away from there. And that's telling you these data are clustered kind of near the middle point. Now, our problem is we have 5 other dimensions. So this E2 through to E6 are all the different ways you can look down on that sphere in different dimensions. The main things to notice are that, first of all, the data is always clustered near the middle and has got outliers further away. And second of all, that the amount of spread in these different dimensions is variable. So if you look at the first one, there's a lot of spread in these 2 directions. By the time we get down to, say, E5, there's only a very little spread in the E5 direction. So this one up through here tells you how does E2 compare against E5. And you see there's a lot of spread in the E2 direction, not very much spread in the E5. This information, whilst it seems completely so deep in the maths and like, what is this relevant for? This information is actually key to how we've made all of this work better. We take a fancy piece of maths. This maths was developed by Janice. She's worked for years and years developing these kind of things. And this is what we call a probability distribution function. Essentially, it's a way of us taking a function that is continuous and fitting it to all those dots I just showed you. And what that means is you can then evaluate it somewhere where you don't have a dot. So you could go to somewhere else on the sphere and say, what's the value of this probability distribution function over here? Oh, well, there's only, if an event happened over here, there's only a 1% chance it belonged in this population. If an event happened over here, there's a 10% chance it happened in this population. This is our mathematical framework for fitting those data. And it's made up of several parameters that you have to worry about fitting to the data. So we have a procedure to work out what these numbers should be and so on. This is so annoying. Yeah, sorry, I don't know why these pictures have all gone wrong. Anyway, we'll plow on and deal with it if there are any questions about it. The end goal was to do a better job of being able to differentiate between earthquakes and explosions. And so what I've now got on this plot here on the right is the result of all of those tweaks that we have made to the methodology, the impact that it has on our misclassification rates. So in the table, you can see at the top, this one here was the pre-existing method. And we looked at that and we saw it missed around about 20% of the explosions. So basically 30 of the explosions that we originally were missing. And we were wrongly classifying 2% of the earthquakes as explosions, which was also many, many tens of events because the earthquakes are so much more numerous. After all of this work, we've ended up down at the bottom here, which is that for the same number of earthquakes that you get wrong, the 2% number, we've managed to get the explosion misclassification down from 18% to 1%. So if we look at that on this loon thing again, you'll see that all the little dots here are events that we correctly classify. The big ones are the ones we get wrong. So you can see these big green ones. These are the 20 earthquakes that we wrongly labeled as explosions. And the two big red ones are the two explosions that we wrongly labeled as earthquakes. So these are the two that are still causing us a problem. Interestingly, this one here was occurred in the 80s, and it's quite famous because the seismic data that we used to kind of image and do all of this moment tensor stuff was really noisy. So it's really low quality, lots of additional noise in there. So it's actually probably never going to work well on this event. The other one in through here, this is actually the smallest event in the whole database. It's actually not a nuclear explosion, it's a chemical explosion, and it was 1 kiloton of TNT equivalent. Now, we were looking at the nuclear tests in the beginning, and they were in the megatons. So they're 3 to 4 orders of magnitude larger than this chemical explosion was. So this is a tiny event, and that's probably, again, why we're not failing to get it right. Ah, yeah, that's those two. So kind of summing up all of that, sorry, I know we really switched gears in the middle of the talk, but that's because I wanted to give you an idea of what's going on in the background of monitoring and then talk about what the actual science that we're doing here is. Basically, I hope that on some level you've understood that you can use the moment tensor for seismic events to discriminate whether something was an explosion or an earthquake. It's not perfect, it still fails in certain cases, and you should therefore use it in combination with all your other discrimination methods. All the things that I talked about that people previously used, don't throw them away, use them all together and combine that information in your assessment. And the last thing, the point I really want to make is that healthy monitoring programs are really key to reducing proliferation of weapons. Now, why is that? It's because through geopolitics, if you know somebody can't get away with doing a test without it being spotted, they're likely to think twice about doing it in the face of international backlash, trade sanctions, or whatever. So a healthy monitoring program, making sure it's funded, the instruments are out there in real time, it's being analyzed, is really key to reducing proliferation. Unfortunately, the way the world's going, it's unclear that proliferation is going to be a problem that's receded into the distance. So right now there is a clear, there's new building work going on at the Korean test sites, at various of the other test sites around the world. It's kind of unfortunate that we've come to this point, but this issue of monitoring nuclear tests is not going away anytime soon. And with that, I think I'll say thank you very much.